my elements on the network, and especially the switches. Now, among those switches, usually you're not going to buy the equipment from a single vendor. You're going to buy from different vendors, and along the time, you'll have different versions of the software of those switches. So for some switches, some of those capabilities, you'll be able to enable them out of the box. For other switches, you'll either need to throw the switch out or to basically upgrade the switch. Think about 10,000 people, think about 15,000 people, think about 1,000, 2,000 switches that you need to play with. It doesn't fly at the end of the day. There's another option to put the client-based software on top of the device. So whenever the client is connected to the network, that basically the client software will tell the server, hey, I'm here. That's another losing approach, and we'll see why. So basically, passive network detection. One of my favorite topics, I actually have published a paper about that back in 2005. There's a lot of material there. The biggest problem here is that we cannot control, or those solutions cannot control what they see on the wire. I cannot make you send email, and I cannot make you open your browser, and I cannot make you do something else in order to draw conclusions from your traffic about your device. Now, the device can also be idle on the network. Printers usually don't send their traffic through routers. They don't. Switches, they'll have their own management networks, and you don't see them sending traffic through through routers. And there are other devices at the end of the day that are being approached and are not approaching other systems. So basically, if I cannot control what I see, and if I cannot control the pace of the discovery, it means that I cannot discover everything that is onto the network. So if I connect locally to that network, don't broadcast any traffic if the listener is at layer 2, basically I will not be detected. And if the listener is at layer 3, it's even worse, because I can do whatever I want on the local subnet and nobody will know that I'm there. This is a good example to illustrate the problem. Usually there are two ways of doing this. First, there's a broadcast listener that is usually a local software installed on one of the servers and listens to broadcast traffic only. And another option is to insert either an inline hardware or actually put an out-of-band solution that is connected to the switch and gets passive traffic. As I mentioned earlier, the layer 3, first and foremost, it's not real time, because if something is connected to the network, we cannot make that something actually send the traffic through the router or through that specific monitoring point, and access to the local subnet will be given. Nothing can be done against it. At layer 2, we can do other tricks. Two examples. One of them is with Cisco Clean Access. This is actually taken from the original presentation. The problem here is that the detection of the device is actually being done here at this stage. Now you can see that from the device to the actual component here, the device may connect through wireless, the device can connect through many hubs, the device can do whatever he wants or she wants. Well, it's actually the user, it's not the device. So if the user wishes to access anything that is not controlled by this server, it can do that, no problem. There's nothing that actually blocks the device from doing so. Another example is again with Cisco. And this is, again, a slide from their slide deck. Here you can see that the solution is actually being enrolled throughout the branches and throughout the data center. And the presentation basically says that you can basically defend only the data center and you don't need to do anything at the branches. Can someone tell me why this is not such a good idea? What at the end of the day goes down? Let's think Blaster. What did go down? The access, not the core. Because Blaster showed us that a simple worm with ping capability basically can bring down the switches, the access switches. From experience, I can tell you that a lot of companies had internet connectivity running. That was fine because the core switch survived, but all the access basically failed. So what we want to avoid is we want to avoid a situation in which in a certain branch which may have an important data or still may have a lot of people, someone will connect, will not be identified, and would be able to do whatever she wants, and still infect the elements, steal data, do whatever. So if I concentrate my defense only at the data center, then I miss all the branches, and not always the branches needs to go through the headquarters for internet access. So in that respect, I don't control anything rather than saying that I control just the stuff that goes through the data center. Is this understood? Another interesting example is all with the broadcast listeners. The idea of a broadcast listener is that whatever we send broadcasted will be heard by the broadcast listener. The problem here is that we can actually change that quite easily. Instead of broadcasting the traffic with, for example, the ARP example here, I can send unicast ARP requests and not broadcast ARP requests. Everybody that will receive that will be more than happy to reply to those requests and will send me the replies. So in that way, I can actually communicate with the router without any problem, receive the router's MAC address, and surf to the internet with no problem at all. So the broadcast listener would not even understand that my device is onto the network and would not be able to defend the network against what I'll do. Well, this is just a simple example for the broadcast listener, but we will see later on an example for the broadcast listener plus an inline device and a combo, and we'll see how we can bypass them as well. Other examples, DHCP. On DHCP, usually they put the solution put a DHCP relay server basically in front of the original DHCP server. That DHCP server actually gets the DHCP requests, hands non-routable IP addresses, and after the NAC process, it basically allows the request to get to the original DHCP server, and there's a renewal of the IP address. This is another bad example of element detection, because if I configure my machine with a static IP address, nobody knows I'm there. SNMP traps. There's a trend especially on Cisco gear, to turn on a trap, which basically says that a new element is connected due to the fact that a new MAC address is registered on a certain port. This only works if your switch actually has this capability in its software. The problem here, as I mentioned earlier, is with the switches. Where are they in the first place? And the second thing here is that if you don't know your infrastructure, then you have a real problem of doing this. The second thing that I wanted to say about this, is basically that the fact that the SNMP trap is being sent, but the time to process the SNMP trap is also a problem. Because usually you'll have a gap that for some equipment will go between 30 seconds to even 2 minutes before the information about the SNMP trap will actually be processed by the management server of that particular solution. So the gap here is between 30 seconds to 2 minutes that element can do whatever he wants on the network. How fast did it take to send the SQL worm? How many packets did the SQL worm had to send? Someone knows? Only one packet. So 30 seconds to 120 seconds, that's a no-go, because we need to block the access as soon as the device enters the network, rather than to wait for something to trigger that and allow it a window of opportunity to do whatever it wants on the network. On the client software, again, client-based software that cannot be installed in certain operating systems, and again, you're vulnerable here. Other things that will not go into how you defend from NAT-enabled devices, how you detect NAC. Virtualization makes a huge problem here. Because basically if I have a device with VMware, with Xen, with Parallels, with whatever, and I launch it in NAT mode rather than in a bridge mode, usually nobody will detect the presence of that operating system. Questions? Yes? Yeah.
There are devices which do not usually allow traffic to pass through if you have not used BGP. So you could block those events.
You refer to basically DHCP protection that some switches may have. The problem there is that on paper it looks very nice. The problem is that if you don't control each and every switch and you filter on each and every switch, that doesn't work. Because it's only good, it will fail if you bring a switch that is not configured that way. And if you don't control your entire environment, then the access list that you have to introduce on each and every switch basically will not do that work because your traffic will still be able to be sent. Another issue with that is that as your organization's internal network goes bigger, your ability to actually control the switches or control your elements is basically lowered. So in that respect, if you want to make sure that all of the configuration actually is where it needs to be, you need to know your entire infrastructure in order to do so. But that's a valid defense, actually. Validation is the process of authorizing devices to operate on the LAN by identifying their identity of the devices and of the users. The idea here is that we wish to combat rogue devices. This is again tied with the element detection features. And at the end of the day, this shows us why we must immediately block any rogue element that tries to connect to our network. The problem here is, again, I mentioned that earlier, not all of the NAC solutions will actually authorize devices. Actually, most of them will not. And basically, since they lack the ability to understand the contextual network information, the time gap that a certain element will have to do whatever he wants on the network, or the user will have, is quite substantial. On the other hand, if you look at those solutions that mandates only user authentication, then there's a problem here as well. Because at the end of the day, what we actually can do is we can bring any type of hardware we would like, use a username and password that is valid to the NAC solution, and gain access to the network with a rogue device. So technically speaking, this is easier stealing a user's identity, or for example, bringing my laptop from home, multiple connect several devices, and do whatever I want on the network because I have a username and password that is valid to the network access control solution. Another example, same slide. You can read what is in the middle. Network access is blocked until the end user provides login information. There's no relation whatsoever to the endpoint here. Basically, you bring your device, you browse, you're presented with a nice captive portal telling you download this agent. You download the agent, you put your username and password, off you go, you're okay. No problem. So in my opinion, tying between the device and the user is extremely important. And it basically creates a binding which is needed for stronger authentication, authorization, and of course for auditing. And an identity is something that we all are looking to have stronger and stronger in our organizations. Another quite interesting example, it's with DHCP replacement servers. Basically, I call this DHCP in a box. You get a DHCP replacement server. The way this works is you request an IP address, you get a non-routable IP address, you're redirected to some kind of an authentication portal. The authentication portal requires your username and password. You provide your username and password. The information is being checked against a user data storage. And that user data storage basically verifies or not your authenticity of the user. And there might be other checks to follow. And at the end of the process, if the element is compliant, then the DHCP server provides a real IP address to the device. What's the problem here? Old attack. I just installed my Linux machine, configure DHCP server, and this is a race. If my DHCP server answers first, the user will use my DHCP server. And I build my own captive portal, the same as the captive portal for the organization. And I provide, as well as user data storage. And basically, I steal all the usernames and passwords. So technically speaking, this is an attack from the old days that I can use here. And why is this even much more problematic? Because with the username and passwords, I can do whatever I want on the domain, I can access whatever data I want, and I can do whatever I want. So this is why this, for example, is a bad idea to use this type of solutions. We'll talk